For this problem, it is telling you that we are going to do an SN2 mechanism. And so you need to figure out, when you take this compound, treat it with sodium hydroxide, using an SN2 mechanism, which product are you going to get? So on the exams, you'll see this is, say, option A. And then you'll see this as option B. And then you'll see an option C, which is, it will say both A and B. You can't see that very well, can you? Okay, so that marker's out. And so there is only one correct answer for this problem here. And it's this one right there. But why? And to answer the why is that the correct answer, we have to look at it mechanistically. So we said SN2. So that means the sodium hydroxide right here, we can see that that is an ionic species. So that's going to dissociate into its ions like that. And in this example, it's not showing you what solvent is involved. And because we're just omitting that for right now. But yes, there is a solvent. There has to be, because sodium hydroxide is a salt. And you can't just sprinkle a salt on a molecule and expect it to react. It needs to be in a solution. So that's implied. So we have the hydroxide. And how is that hydroxide going to react with this alkyl halide? Well, we're told it's an SN2. And first, though, we take a look. This is the halide, which is a good leaving group. What degree of alkyl halide is that? We see that that is a secondary alkyl halide. And can secondary alkyl halides undergo SN2 reactions? And the answer is yes. And so mechanistically, what is the SN2 mechanism? It's going to take the hydroxide. It's going to come in backside attack. So that means on the opposite side of where the bromine is. So if the bromine is in the front because it has the wedge, then that means the hydroxide is approaching from the back. And if it's approaching from the back, then it's going to be a dash. And so the OH right here is coming in from the back side, which is a dash like that. And so what does that do to the dashed hydrogen here? That is now going to invert it into a wedge like that. And so you can see here that the configuration of this is what? Let's do the configuration real quick. So that is an R. And now look at the configuration. 1, 2, 3, R. So that has to be an S. So we inverted the stereocenter. And so that would be the only product. You are not going to get a racemic mixture. It's just one. A racemic mixture is a 50-50 mix of A and B. So that's the mechanism. And I hope you see that the mechanism helps you figure out what the product or the answer is going to be. It shows you what the product is. So learning mechanisms is a tool for you to use to predict products. Now we have a problem where it's asking you predict the product. And in the question, you're given a hint. You're told that it is a SN2 mechanism. So now because you know the mechanism, you can predict the product. You may not know what it is off the bat by just looking at it, but that's why you go through the mechanism to figure it out. So how do we do this? Well, we double check. What type of alkyl halide is this? That is another secondary alkyl halide. And so that works for an SN2. We see sodium, which is a metal, and then sulfur, which is a nonmetal. So that's an ionic species. So that looks like this when it's placed in solution. Once again, the solvent is implied because that's going to be a solid. And so we take this, and how does the mechanism work? Backside attack. So this has to come in. And drawing the arrows, it's impossible to show that it's coming in backside, but you know it is. And so the leaving group leaves at the same time as the nucleophile comes in. And so based off of that mechanism, the sulfur, which is still attached to an H, has to come in from the back. So that's our S. It's using this lone pair to form this dashed bond. And it still has two lone pairs that are not being used, and it's attached to a sulfur. So that's going to invert it. And so now the hydrogen is now a wedge. And this wedged methyl is still intact because this nucleophile did not attack that carbon. So it didn't invert that stereocenter. It inverted this stereocenter, the very stereocenter that the sulfur atom attacked. And so based off of this mechanism, that would be the only product possible. Only one. If I did draw this one right here, like this, if you drew that as a product, then that's 100% wrong and is not even possible. Why is it not even possible? Because you see the leaving group is a wedge, and then the nucleophile that's coming in is a wedge. So the only way, if this reaction did in fact work, that would come in from the front side. That would be a front side attack. And we've learned that SN2s do not do front side attack. This is backside attack. And that's how SN2 mechanisms work. In this problem, you are asked to do a SN2 mechanism to figure out the product here. Now, when we look at this, we know that in order for us to do an SN2, you need to have a group, typically an alkyl halide, that can leave. So when we look at our molecule here, we have a methyl group. Is that a halide? Nope. And methyl groups are bad leaving groups. No go. Then we look at this functional group right here. What is that? That is an alcohol. Are alcohols good leaving groups? No, they're not. So if you were given this as a problem and say predict the SN2 product, you would say no reaction. That is not possible. Why is it not possible? Because we don't have a leaving group. But what's the cool thing about alcohols is that if you add a little bit of acid, you can protonate that alcohol. And if you protonate it, doing acid-base chemistry that we have learned in previous chapters, what's going to happen? It is now positively charged. Now, when oxygen looks like this, can you see what it kind of looks like? An oxygen with a hydrogen and a hydrogen. That's H2O. So once we break this dashed bond, this piece right here turns into water. So what you could do is make the analogy that this molecule, let's see if we can get a different marker here. Nope, still not very good. So what you can say is when an alcohol is protonated, It's analogous to a halogen like bromine or iodine or chlorine. It's analogous. So if this was the problem, well, let's change it to chlorine for right now. If this was our problem and we had bromide right here, what would the product be? Not having much luck with markers today. Okay, nope. If we did an SN2, that would give us this as the product, right? There you go. That's what we would get if this was doing an SN2. So the same thing happens when you have a protonated alcohol. You treat it just like a halide. So that's going to come in, backside attack, and the leaving group leaves. And when that leaves, you're going to generate the backside attack. And so backside attack simply means the opposite orientation as the leaving group. So now in this case, the to be attacking as a wedge because that's the opposite side of the molecule to the OH group or the water molecule. And so we would have our dash hydrogen still, and then what fell off? Water. So that's would be our main product right there. And that's the only product that we're going to get. But yeah, that's the big kicker here with this example, that this is equivalent to halogens because it's a good leaving group. So in this reaction right here, we're told it's a SN2 mechanism here, but I'm going to change this right there, okay, to a CH3. Okay, now, what would the product be of an SN2 reaction for this? Okay. So bromine is on a wedge, so that means when this gets dissociated in the solvent, we know that that's going to be this. And so if we draw it mechanistically, we know that we do backside attack. So we would expect the sulfur atom to come in from backside, which is like this. And then what happens to the wedged methyl, or sorry, the dashed methyl? That's going to get inverted, right? Into CH3 like that. Okay, let's take a pause here. The arrow makes sense, backside attack, leaving group leaves, all in a concerted fashion. But if you put this as your answer for this problem, no go. That is not correct. Not in the least bit. Why? The mechanism arrows look good. Well, it comes back to what type of alkyl halide is this? That is a tertiary alkyl halide. And what have we said about tertiary alkyl halides in regards to SN2 mechanisms? They do not happen. And so the correct answer for this problem, you would have had to have written no reaction. That is the correct answer. So that is something that you always have to watch out for, class, is the degree of the alkyl halide, or if we changed it to OH2 positive, that's water, and that's a good leaving group. Can this happen via an SN2 mechanism? No, because that's still tertiary. So what you're doing here is whatever the leaving group is. The leaving group could be water, it could be a halogen. So let's just say Lg for leaving group. If the carbon that the leaving group is attached to one, two, three other alkyl groups, that makes that tertiary, hence no SN2 reactions. That does not work. Now, does this molecule right here, can it still undergo a reaction? Yes, but not an SN2 mechanism. All right. So in this example right here, where we have a secondary alkyl halide and we have hydroxide, and I tell you that this has to undergo a SN2 mechanism, what would the predicted product be? Well, we can do it mechanistically, which is the best way to do organic chemistry. That is an SN2 mechanism. So that means our OH is going to come in dashed like that, and then our chloride is just going to be floating around. That's what's happening mechanistically. But I have the model here. You can see that everything matches up. Do you see the zigzag right here? Do you see how the zigzag right there, that carbon is pointing down? So that carbon that I'm pointing to here is this one. And then there's that carbon, which is there, and you can see that we have a wedged chlorine, which I'm representing with this blue atom. All right, so can you see that there? And then this carbon is that carbon, or that one, this one, that one. All right. The zigzag matches the model. So if you guys pull out your model kit to do this on your own, you need to make sure the orientation matches my orientation here. Now, let's draw the incorrect product. The incorrect product would be this. Now, why is that incorrect? Well, I have here in my hand a red atom, which is going to represent the OH. So that whole OH thing is going to be just represented by this single red sphere. Right? And I'm doing this just to keep things simple. So in order to get this incorrect product, how would this atom have to approach the molecule? It would have to approach from the same side as the blue atom. And that would be front side attack. Whereas you have to take the molecule, instead of, it's going to have to travel all the way around to the other side of the molecule and come in from the opposite side of where the blue atom is. And that would be backside attack. And so since this red atom, or we'll call it an atom, or this red sphere is coming in from the back side, so from your perspective, that makes it a dash. But if it approached from the front side, then that would give you this. Now, remember, front side, back side is all in perspective to where the leaving group is. If I took this molecule and rotated it like that, now the blue atom, or the chlorine, is sticking away from you. So think about this. The way this red atom is approaching, is it backside attack or front side attack? It's going to come and attack here from that angle. That would be what? In contrast, if we take the red sphere and it comes all the way around and attacks this side, how would we classify that? Do you have your answer? All right, here's the answer. If it comes in this way, hopefully you can see that it's on the opposite side of the blue atom. Hence, this would be backside attack. And then if we come from this direction, we see that the red atom and the blue atom right there are on the same side. And that would be front side attack. And we don't do that. Okay? So hopefully that makes sense and you can see that well enough in the video.